Okay, so I'm illustrating in this case how to come up with your what's called your simple linear regression equation. And this is number 13 from your textbook, but it's the same data from basically exercise number 1, which I've already shown you. So if you kind of go down here, I'm just going to reference this real quick. You can see this tabular box is essentially the same answer to exercise number 1 when you had to calculate your correlation coefficient. So we're going to go back. We're basically going to be using that same tabular approach. But in this example, I'm not going to go back and walk you through again how to get the correlation and how to set up these numbers. I already did that in the previous example. But I just want to show you how we're going to actually use the same data that we already calculated for the correlation coefficient to actually develop our linear equation. Okay, now let's go back. Our linear equation is simply stated like this: y equals a plus bx. Okay, so b is going to represent what they call your slope. Your a is going to represent what you call your y-intercept. That's just the label for it, and most of you probably can remember that from your math classes. Now, let me go back. So to calculate a slope, and I'll keep the equation up here just to kind of keep reminding you this is what we're dealing with. The calculation for the slope goes like this. You take your correlation coefficient, which we've already calculated. This is from exercise 1, which is the same data, multiplied by the standard deviation of y divided by the standard deviation of x. So we already actually have the numbers. We just have to plug it into this equation to get the slope. Okay, it's really, really that simple. So at this point, if we did that, we said that the correlation we said was what? It was 0.75 approximately. I think they rounded this a little bit farther on this one, but let's start with 0.75 multiplied by the standard deviation of y, which in this case, I'll just use the number from this particular problem so you don't get confused. It's about 1.3, but 1.304 is what they're using, over the standard deviation of x, which is about 2.702. And again, if you go back to the exercise number 1, I think they didn't round. They rounded a little bit sooner than this one. Don't let that mess you up. But if you were to then calculate that, that's going to give you a slope that is approximately, I'm going to write this at approximately 0.363. Okay? Now, so that's going to be the b value. Okay? Now, once you have that, now you can then solve for what they call your y-intercept. And the way you're going to solve for your y-intercept, which is again represented by letter A, is what you do is the formula is you take the y bar minus the slope multiplied by x bar. That's the formula to how to get the y-intercept. So if the y-intercept, if y bar was 5.8 minus the slope, which again was 0.363 multiplied by x bar, which is about 5.6, just plug it in. That's going to give you a y-intercept of about 3.767. Okay, so that's basically, here's step 1, this will be step 2. Now, once you've done all that, now you can simply plug it into your equation, which will be y is equal to, in this case, 3.767, which is your y-intercept, plus your slope, which we just said was 0.363 multiplied by x. So that would be your answer to letter A. And then the second question says, determine the value of y when x is 7. Well, that should be pretty simple. You just got to plug it in for x. So you'd say y is equal to 3.767 plus 0.363 multiplied by 7. And then now you just multiply it out and solve it. So, and then of course, once you do that, they give you the answer down here at the bottom, and the answer is about 6.3081 approximately. That would be your answer. But the basic idea behind this is back from illustration example number 1, to get this linear equation, you still have to go through the same setup that you did to get your correlation coefficient. It's basically you got to go through the same steps. All right. Now, one more thing I do want to show you. They didn't ask you to do it, but something that may show up in some of the homework is there's a value that's called r squared. Okay, and it's real simple. If our correlation, in this case, we said, this is again from illustration 1 and this particular example, it's right here. If our correlation coefficient is 0.752, if you square that, you're going to get what's called r squared, or coefficient of determination. So for example, if you took 0.752 and squared it, you would get about 0.5655. And what that basically number means is it's an attempt to explain how much of the variation of y is caused by x, because x is that one variable you're using to see about the independent dependent kinds of cause and effect relationships. So if I go back to this simple equation, again, this r squared is trying to say, okay, how much of y is affected by this variable, by this volume, whatever activity level you're using. And the higher the better. So if you get 0.5655, you're basically saying about 56% of the variation of y is caused by that one variable. And if you're doing a study, that may not be a good number. Typically in the business world, you'd like to see r squared numbers approaching 100 or 1 or 100%. But typically, if you get r squared numbers like around 0.8, 0.9, you pretty much know what causes y. You know that one variable is having a big impact on the y variable. Okay, so it's just another quick calculation, because you can get correlation coefficient already based on the calculations. To get the coefficient of determination, you just have to square it, and in this case, that's all you have to do. Now, the textbook takes you through a very, very detailed, complex way of also, there's another way to calculate this number. I'm not going to make you do that. I'm not going to test you on that. As long as you can get the correlation coefficient and then square it, that's something you will probably need to know for the exam as well, as how to get what's called the coefficient of determination.